My name is Anthony Noguera, and I lead the Business Applications AI team at NVIDIA. Today, we will talk to you about how we achieved supply chain responsiveness and stability at NVIDIA using operations research and artificial intelligence. We will begin with a video from Shweta Singh, who heads the supply chain planning organization across all products at NVIDIA. She will describe NVIDIA's supply chain challenges and how our project made a significant impact to NVIDIA's supply chain performance.
Here's what NVIDIA's supply planning journey looks like, from planning chips to fully integrated rack-scale systems in AI factories. The scale and complexity, it's unbelievable when you plan a full ecosystem. The GPUs, the switches, NICs, cables, they all have to come together seamlessly with end-to-end precision and optimization. I talked about scale, but the other impact on planning has been reliability and efficiency. On reliability, our on-time delivery performance that is industry-leading, aided by continuous optimization in the area of customer product allocation. Moving on to efficiency, our business had outgrown what our legacy planning systems could handle. So with our planners using AI planners, we've seen a 6x increase in planner productivity, with new agentic capabilities still being built into it. The AI planner has become our foundation to build scalable supply chain intelligence. This tool enables domain-specific skills that support adaptive agents, allowing us to build, refine, and extend decision intelligence. The journey from manual optimization to intelligent decision systems has been transformative, yet it feels like we're just getting started. It's driven by agentic workflows, long-running autonomous agents, and systems that continuously learn, adapt, and act with purpose at scale.
Let's look back at NVIDIA's journey as a company. Many of you know, as a company that invented the GPU back in 1993, which sparked the PC gaming market and pioneered accelerated computing, we are no longer just a GPU for gaming manufacturer. Today, as a global leader in accelerated computing and artificial intelligence, we are building the world's AI infrastructure. These power that we now call AI factories or data centers purpose-built to produce intelligence at industrial scale. If you look at the progression from left to right, you can see how staggering this platform shift has been. Over the last decade, we evolved from manufacturing single-chip video accelerator GPUs to creating our first configurable general-purpose GPUs like the P100 and the A100. Today, we have made another massive leap to engineering full rack-scale AI supercomputers like the DGX, HGX, and GB200 systems. To physically deliver these products, our operations had to expand massively. We now rely on hundreds of partners to deliver thousands of different components to a dozen factories in order to build nearly 3,000 distinct products. Today, we manage a highly complex global manufacturing network that spans dozens of locations across 3 continents. At this immense scale, a single disruption to our supply chain can severely impact our ability to meet our commitments to the market. Managing this complexity isn't just an operational challenge, it's a planning challenge. Every leap in product complexity you see on this slide demanded a corresponding leap in how we plan, coordinate, and optimize our supply chain. Now let's look at NVIDIA's supply chain planning tools journey. When I joined NVIDIA in the early 2000s, we were using basic APO and spreadsheets for supply chain planning. The Demand Supply Network, or DSN for a graphics card, our main business back then, was a simple sequence of manufacturing activities with a limited number of parts and customers. As complexity of our DSN increased, we built and implemented a sequence of more complex SAP APO models with built-in solvers in the mid-2000s. Somewhere in the mid-2010s, we started transitioning into in-house central planning models using commercial solvers and custom wrappers. Our initial focus was wafer starts and allocations to customers. As complexity of our DSN exploded even more while we were delivering fully integrated rack-scale AI factories, we doubled down on developing our in-house central planning models. At the core are unified MILP frameworks that capture the end-to-end supply chain complexity and input data structures that feed the models from our SAP and other legacy systems. In the rapidly evolving supply chain planning at NVIDIA, we started building agentic workflows to make operations research more accessible to our business planners without more specialized OR expertise. The future of planning is agentic. Tools, knowledge like embedded OR expertise and reasoning converging into continuous workflows that ideate, execute, and validate. This enables planning systems to monitor, understand, and formulate a response while a human planner is offline, presenting pre-validated plans for them when they return. Now let's hear from Alvaro to describe NVIDIA's demand-supply network.
Thank you, Anthony. This is a simplified representation of NVIDIA's supply network. It starts with wafer planning, which secures adequate wafer commitment quantities and specifications for production. Wafers are then diced and assembled with other procured materials, memories that are planned in advance, interposers, and substrates to produce the GPU chips. From there, the flow branches. Chips are used for consumer gaming systems or assembled into boards that fit the latest generations of data centers and AI supercomputers. Coordinating all this is the NVIDIA Central Planning Engine. It synchronizes the flow of information and planning signals across each of these domains. Teams planning wafers, planning procured materials, teams planning chip production, teams coordinating turnkey materials for data centers, and teams translating demand into production plan requirements. Each operate with its own optimization models, but all are synchronized through the Central Planning Engine using a shared set of constraints. The problems these models solve range from demand coordination to throughput maximization. Product allocation assigns open production orders to effective demand. Availability versus committed coordinate the final efforts to generate finished goods at the last step of the supply chain. And max supply determines the maximum production quantities per finished good. Today, we'll use max supply as a running example throughout the presentation. At NVIDIA's scale, every planning decision has a direct impact on how many racks and AI factories reach customers and when. If the right part exists but sits in the wrong location at the wrong time, that is a rack that could have been built. Max supply is how we make sure it gets built. The objective is straightforward: maximize production of weight finished goods. This is given a fixed wafer supply. How many boards and systems can we build? The model operates on a hybrid pull-push basis. Production is pushed for products in the requested build plan, and pull, which is waiting for a signal, for derived products. Procurement adds a critical dimension. The model runs under both unconstrained and constrained scenarios. Unconstrained shows the theoretical maximum production capacity, while constrained reflects the scenario where supply is limited. The key insight: the model surfaces what's actually constraining the production. For example, it might reveal that a specific procured material sits on the critical path, limiting output for an entire production family. And it shows when and whether we can catch up with the theoretical maximum production. This is why planners run multiple what-if scenarios. The answer changes depending on what's constrained. A memory-limited scenario produces a fundamentally different plan than a chips-limited one. Together, these scenarios form a sensitivity analysis that gives executive a clear view of where the plan is fragile and where it is robust, directly supporting procurement and replenishment decisions. Now, let me show you what is under the hood. Beyond the mechanics of max supply, this slide shows the additional constraint categories that I mentioned earlier. These aren't specific to max supply. They are a shared set of constraints governing essentially all the optimization models synchronized through the Central Planning Engine. Let me walk you through how they connect. It starts with structure. Multi-level BOMs map every required component across the production hierarchy. But beyond being multi-level, each product can have multiple BOM entries, meaning there are multiple production paths to the same finished good. Production ratios then determine how input flows through each of these assembly stages. Then variability. Time-dependent yields adjust material quantities based on process efficiencies, and this yield shifts period to period. Interchangeability operates at two levels. At the finished good level, one product can be alternated with a similar product with minimal adjustments. At the component level, parts may have multiple substitutes when supply is constrained. Then, the physical reality. Co-production means a single input, like one wafer, yields dozens of different die beams, all of which must be tracked even when they are not immediately needed. Production is bounded by resource capacities, and location and transferability constraints enforce where materials can be built, stored, and moved. Adding to the complexity, many of these variables are date effective. Bumps, yields, capacities, interchangeability rules all fluctuate over the planning horizon. The solver must align these temporal dependencies to generate a feasible plan. This constrained architecture supports the central planning engine's orchestration with a holistic network representation of our supply chain, scaling beyond wafers to include memories, turnkey components, networking cables, and structure. To discuss the engine that processes this constrained architecture, I'll hand it over to Alex to introduce co-opt.
Thanks, Alvaro. Hi, I'm Alex Fender. I'm the Director of Decision Intelligence at NVIDIA. And operation research is not just critical to operation. It has infused and transformed NVIDIA software and hardware. When I joined the company 12 years ago, we were mostly known for gaming. Since then, GPU accelerated computing has transformed industry after industry. So when our supply chain was hitting limits, we made an opinionated choice. We designed the full decision pipeline to run on GPU. We pointed the same technology that we built for the world at ourselves. On the journey, we learned that many operations research fundamentals apply for the GPU. The operation solver matters, but so does everything around this. We couldn't just tune an algorithm. We had to eliminate latency across the entire pipeline. Data extraction, matrix construction, pre-processing, that alone gave us an order of magnitude of speed up. Faster speed means more scenario, larger models that capture the complexity of reality. When your pipeline is fast enough, you just don't optimize an old process, you plan continuously. And that created a flywheel at NVIDIA. We're NVIDIA, right? So the hardware software co-design is core to what we do. Hardware, math libraries, data pipeline, solver, agents, all evolving together. Every improvement multiplies through the stack. So more concretely, our supply chain problems are large. They are also sparse and tolerant to approximation. That profile pointed us to PDLP, a first-order LP method that maps naturally to GPU parallelism. It solved our problem faster, right on our own hardware. But the sparsity pattern in our LPs didn't match any existing libraries. So we rewrote the sparse matrix vector multiply tuned to those parameters and patterns. When we hit models that were not suitable for first-order methods, we built a Cholesky factorization for the interior point method, and we made it deterministic across thousands of threads running in parallel. On the MIP side, we are building a GPU-native solver focused on primal heuristics. Finding feasible solution is what matters when agents drive the optimization loop. The hardware keeps moving too, and maybe that's the most exciting part. Optimization and data processing scale with the memory bandwidth. And the memory bandwidth just doubled in the last GPU generation. Every new chip delivers direct speed up to the software at a velocity we haven't seen in CPUs for decades. As of this month, linear programming is even part of our hardware performance benchmark and validation process. Before we even produce a new chip, we make sure it's good at our supply chain problem and operation research. We didn't build this alone. We partner with the solver community to improve this stack together. PDLP's recent algorithmic improvement come from MIT, and the pre-solve work comes from Stanford. We even work with Microsoft, who is a finalist of the French Edelman, to make agents smarter. Finally, we design how agents interact with optimization solvers. Without guidance, agent wanders. They burn token at guessing. And so co-opt chips with tens of skills that tell the agent exactly what to call and what to do with the results. That means fewer tokens, faster run times. So the solutions the agent couldn't reach on its own is now within reach. The pipeline we built gives our planner superpowers to run scenario, compare trade-offs, and decide faster than ever before. And this is where our story goes next for technical details with Jing. Thank you.
Hi everyone, I'm Jing. We have the mathematical assets and we have the high performance solvers. In a perfect world, that would be enough. But in reality, there is still a hurdle we call usability paradox. The paradox is that even though the math is more powerful than ever, it is often locked behind a wall of technical expertise. To leverage it at the heat of the moment, a planner still needs a small army of specialists. We see this plays out in two main bottlenecks. First, there is data gap. When live system hasn't catch up with reality, the planner ends up manually scrabbling data just to keep the model from breaking. It's ridiculous. It's the magnet for human error. Second, there is strategic pivot. A business goal change, like prioritize speed over cost, the planner has to call the OR scientist to reformulate the logic or reconfigure the model. We're looking at a long lead time just to answer a simple what-if question. The reality is to truly leverage the genius of our OR specialists. We cannot have them sit in every meeting just to reconfigure an existing model. We need to move from specialist-dependent optimization to planner-empowered execution. So our answer is AI Planner, which is co-designed with our OR team. It's more than just a tool. It is a collaborative ecosystem where human expertise and machine intelligence need to drive better outcomes for the company. The story all starts with large language model. Think of it as the thought engine that provides intuition to understand the complex inherent intent behind the planner's request. But as we like to say, a brain without hands cannot move needles. That's where the harness comes in. The harness is what transfers a static model into an agent. By wrapping the large language model in a harness, we give it actual power to execute the work through a few key layers. The first one is the database and tools, which gives the agent system visibility. It creates a windows into your repository and data, because even the smartest agent cannot make a good decision without a clear view of the facts. Then we have skills, and this is where our OR specialists really shine. We don't believe an agent should ever guess its way through a multi-million-dollar decision. We know that even the most advanced agent is only as reliable as the model beneath it. That's why we build the skill layer as an evolving, expert, verified knowledge base. Think of this as a curated library of verified OR models, technical instructions, and validated assets. The large language model provides the incredible reasoning speed to navigate the complexity, but the skill provides the anchor. It ensures the agent acts are always grounded in rigorous human-vetted logic, rather than just probabilistic guessing. To manage this safely, we've built the entire system on a foundation of role-based governance. When a business planner logs in, the AI planner is restricted to only pre-authenticated skills. It only uses high-fidelity model assets that our OR team has already approved. This moves the risk of unverified logics or hallucination, so the planner can trust the results and the insights generated. But for the OR scientist, AI planner becomes a modeling teammate. It acts as a specialized pair programmers for optimization, helping brainstorming, documenting, prototyping, debugging, and stress testing the new logics in real time. Once the scientists verify a new model asset through their own expertise, they publish it into our skill knowledge base, making it instantaneously accessible for planners across the organization. It creates this secure, scalable loop. The scientists define the rigor, the planner executes the strategy. We aren't just automating math, we are scaling human expertise across the entire organization. Security is also important to us. To keep things safe, the agent works in the sandbox. It's an isolated workspace where it can run codes, test configuration, without ever touching the live production system. We also care about scale and efficiency. It coordinates a team of task agents. They are specialized to handle heavy lifting like data mapping, coding, or deep dive analysis with professional efficacy. And finally, there is memory. We store the complete work trajectory, providing a transparent trace of every logical step and decision. It is not just providing an audit trail. It's a way for the agent to learn from every success and failure, understand your specific role and intent, ensuring every action stay aligned with who you are, how you work, and that's how it becomes a true partner. Let's go through a concrete example. Say the planner gets to know some configuration, some condition changes in the supply chain. Some additional wafer become available. Supply pull in happens for some substrates, and some progress in the efficiency of system and board processes. But updates are not there yet in the live system. The planner does not need to go to an OR specialist to conduct such an experiment. She could just go to the AI planner where the OR specialist already transferred knowledge to. First, the query refiner kicks in. It refines the request from planner based on chat history, who the planner is, what she cares about. Let's say if she oversees procurements, the analysis will be more in-depth into procurements instead of planning schedule. It also produces results in the format she likes. Second, the agent going to anchor knowledge from OR empowered skills to grab the needed data from the database associated with the task. Now, the agent gets all necessary information to come up with either a comprehensive plan or a clarification question if the request can be interpreted in multiple ways. For this particular example, the plan it comes up is an impact analysis, where it sets up baseline and the what if with all changes required and the final data analysis to understand the impacts. During the execution, AI Planner pulls in a pool of specialized task agents that carry out the task in a secure sandbox, leveraging OR skills, tools, and data. Based on the execution results, it will generate a full report with the step it did, the insights on the results, like the impact on the supply products, market name, procurements, etc. Planners could keep asking follow-up questions to dig deeper, like what drives the changes, where to find the results. The planner could also head towards a dashboard format they like and share with each other during a review board meeting. What does this actually look like in practice? AI Planner becomes an active participant in planner's daily life. Not just a side tool, it handles all the always-on stuff, the scheduled job, data synchronization, and it's ready for those quick questions like what's the status, so everyone stays on the same page. It also acts as a what-if sounding board. When things shift, planner can just ask, what if we do this? Will that help with the bottleneck? The agent can reconfigure the model right away, allowing for rapid, low-risk experimentation. Crucially, it helps uncover why. Instead of just handing you the raw result, it can help contextualize the results. It can identify bottlenecks and trade-offs, turning what used to be a black box to a clear, defensive strategy. This leads to proactive mitigation, where the user and the agent work together to navigate the mess and find the best path forward. By orchestrating data pipeline, the modeling logics, the results interpretation all in one place, AI Planner terminates the constant scrambling between system and teams. This frees up our OR scientists for advanced modeling tasks, the planners for a high-value strategy, instead of both sides has to sit in the room for manual execution. And because AI Planner is always online, it's ready to provide the clarity exactly when you need it. Even that aha moment happens at 2 a.m. in the morning. Let's hear from planner about their experience with AI Planner.
A typical planning cycle begins with the review of the outputs from the overnight optimization runs. We assess key metrics, validate results, and identify any constraints or variances that require attention. From there, we consolidate inputs from the supply teams, review updates, and then align on the priorities ahead of the planning sync with leadership team.
Given the scale and velocity of our supply chain, conditions evolve dynamically. For instance, in a hypothetical scenario, right before planning sync, we might receive confirmation that we have received excess server rack components that require immediate allocation. The AI planner refines the query, selects the necessary planning skills, and identifies the relevant data sets across supply, demand, and control parameters. An execution plan is generated, orchestrating deep agents and optimizers to simulate baseline versus what-if scenario to support planners' decision-making.
In a traditional workflow, incorporating this kind of change will require significant manual efforts. With the recollaboration of multiple systems at the start of the planning day. With the AI planner, this process is handled in real time. The system updates supply adjustment and runs the simulation end-to-end. It synthesizes the results into a clear and action-driven impact report. It then enables immediate decision-making, rather than waiting for manual recalculation. The AI planner reveals that this wasn't just volume increasing. It was a significant acceleration in supply timing, which immediately changed the way we approach planning. For this example, the analysis shows the front-loading of production, with the mass amount of inventory concentrated for a specific week. With that level of visibility, leadership can act on it immediately, pulling in critical components within a matter of weeks.
The AI Planner provides a unified end-to-end view across teams, removing silos and enabling faster alignment and more confident decision-making. Through the visual analytics dashboards, we can compare baseline and what-if scenarios across the entire planning horizon.
What makes it especially powerful is the level of transparency. Every calculation from start to finished systems is fully traceable. We can drill down into specific line items to understand the drivers behind each outcome and validate decisions with precision.
Thank you, Jane. Turning to outcomes of this work. This solution delivered quantifiable value across speed, reliability, and efficiency. NVIDIA values the commitments it makes to customers to deliver on its orders. In an environment where lots of factors can contribute to dynamic supply uncertainty, few orders end up missing their commit dates. The model values customer request dates while adding robustness in commit decisions made across the planning horizon. This directly leads to more stable customer commits and leads to better on-time delivery by reducing the number of delayed commits by 83%. The engine is not just smarter, it is significantly faster. Looking at speed, we broke the usability bottleneck. The planner is able to create and review planning runs 24/7. This compressed our critical planning cycle from 5 days down to just 1. Our teams can run dozens of what-if scenarios in a single meeting or run it anytime. Finally, the models take on more coordination and constraints across businesses to drive efficiencies. By automating complex trade-off decisions, we effectively decoupled our operational growth from our headcount. Even as we scaled into incredibly complex multi-rack AI factories, our planning team only needed to double in size to handle the unprecedented volume. Ultimately, the integration of operations research, GPU acceleration, and agentic AI transformed our supply chain from a constraint into a strategic engine of growth. What we have built is a way to put OR expertise in the hands of every planner, not just the ones with an OR expert nearby. Our OR teams did the work of transferring knowledge into skills for agents to leverage. The planner gets the benefit of it on demand whenever they need it. That's the unlock. What I want to leave you with is this. The pattern itself is what's powerful. An always-on assistant grounded in deep domain expertise that meets the planner where they are. That's not specific to production planning or even supply chain. Anywhere OR expertise is being applied, scheduling, financial planning, resource allocation, this same pattern can bring the expertise closer to the people making decisions every day. For this pattern to apply, we need the same recipe as we need in every OR-centric product development. Domain context, data foundation, well-configured model assets, and metrics built with the help of OR experts. We also need result storage and sharing mechanisms. The agentic AI helps translate planner scenarios into configurations or understand the results by going deeper and comparing scenarios. Wherever there is a planning function and wherever there is expertise that isn't reaching the people who need it, that is how we close that gap. Next, Rama Akiraju, VP of Enterprise AI, will share the journey and vision for agentic supply chain systems at NVIDIA.
NVIDIA's supply chain is defined fundamentally by a timing challenge. Demand changes weekly, but supply, on the other hand, needs to be procured months in advance. Now, as part of scaling, we are also pivoting from building chips and deploying chips to deploying large-scale AI factories. For example, if you take NVIDIA's Grace Blackwell NVLink 72 system, it has over 1 million parts. Imagine the complexity of managing such a large supply chain operation. We used to take several days to plan this earlier, but now with NVIDIA technologies that we have built internally, including the accelerated compute, cuOpt, NVIDIA's Neutron models, and the AI agentic solution that we have built, we're able to bring the planning down from several days to minutes. AI Planner is NVIDIA's GPU-accelerated agentic supply chain system. It is for our NVIDIA operations teams to effectively plan the broader supply chain network systems from build to deployment planning. Our AI Planner has been in production across 3 different systems since 2024. That's in unified supply chain optimization, fulfillment sequencing, and commitment planning. What took our boards and systems planning cycle 15 hours across many manual handoffs now takes 15 minutes. In a deeply connected, fast-moving environment, speed is of the greatest asset. A tightly coupled solution for planning rack-scale AI factories isn't available on the shelf. So we had to build it, and we had to bring together domain experts from hardware, software to build a solution. The real breakthrough came when all these technologists worked side by side with our supply chain leaders, ultimately augmenting human expertise with agentic intelligence. The next evolution of this initiative is to integrate our supply chain with continuous long-running agentic workflows, along with the open proprietary models, optimization engines, and acceleration libraries.
Rama is our VP of AI Enterprise, but before that, she was also an operation research scientist for decades, and she presented at Inform many times. So she illustrates really well the synergy we are seeing between all those disciplines at NVIDIA. Jensen Huang, our CEO, is also passionate about optimization. He couldn't be here today, but he said this at Computex, and he wanted his community to hear it too. And let me tell you what's behind those words. What does our supply chain actually deliver? The foundation of the world's AI infrastructure being built right now. When someone needs a gigawatt data center, nobody gets to sleep on it at NVIDIA. A single campus is tens of billions of dollars. There are dozens being built right now, among the largest construction project in history. It's on the scale of the Apollo program. A couple of companies placing these orders are even here today, and there are many of those largest companies in the world. We need confidence in that planning, and we need it fast. You saw the operation, research, and the technology that makes that possible today. Thank you.